Karen?
Yes.
Karen, Jonathan, I'm really sorry to interrupt, but yes, could you please move the camera so we could see you? I'm
I
much more
cannot
interested.
because I can't write on the tablet and
Oh,
also move it.
okay,
I'm
got
sorry.
it.
I guess I need to have a separate camera, but I don't have that. I have a tablet that's, the laptop is the tablet.
Understood. Okay,
I
thank
can
you.
just turn off my camera and then that won't look weird. I can hopefully turn off my camera. There. All right. So what is my overall context? So I want to start with a graph, and well, the graphs that I'm most interested in are these ones where K is some 4 regular graph and G is K with 1 vertex removed. Those are my very favorite graphs because I want to think of them as scalar Feynman diagrams. And so if you have the graph, so here's a whole bunch of graph, and if this guy here was K, so here's a vertex, here's another vertex, here's another vertex, here's another vertex, and there's just more graph in here, then what do I want to think? When I think about removing that vertex, I don't really want to think about it going away completely like that, but I want it to leave half edges here. And then in the Feynman context, you think of these half edges as, or external edges, as representing the particles that are coming into or going out of the system. And so the graph in the middle represents some particle interactions, and there's, in this case, 4 particles entering or exiting the system. And so these are my favorite graphs. They come from a scalar Feynman, scalar quantum field theory, where you have, so you have just a 4 regular vertex, and I like having 4 external edges. Okay, now what am I going to do? I want to make the Kirchhoff polynomial of this graph. So I'm going to call that capital Psi. And what is it? It's going to be a sum over all the spanning trees of the graph. And you take a product of the edges that are not in the tree. And now you put you make a monomial of the edges that you would have to cut to build that tree. So I'm going to associate a variable AE to edge E. And so then I get an expression like that. And now the period of the graph is the following integral. So morally, I want it to be this integral. But now if I write that in calculus, you're not going to give me a very good mark because I've left out some important things to actually define this integral. So I would like to integrate over all the variables from 0 to infinity. And now you can think about this in 2 ways. So if any of you in the audience are algebraic geometers first, I think you should think about this as a projective integral. And so then I want you to put a projective volume form up here. But let's just explicitly take an affine piece just to keep it elementary here. So I'm going to set one of the variables to 1. Let's say A1 equals 1, and then integrate all the rest of them. Okay, so that's a thing you can write down. And despite the fact that basically all my talks start with this integral, I don't actually like integrals, but I don't have to think about this in terms of analysis because this integral is strongly controlled by some combinatorial things. Most notably, in fact, this polynomial. Because, I mean, what is this? This is really just, I mean, you can think of it in a number of different ways, but it's just counting the spanning trees where you keep track of which edges you've had to cut. Okay, so that's a little bit, that perhaps needs an example. So let's do a couple of things in an example. Let me just switch colors here. So let's just make sure we got this Kirchhoff polynomial sorted out. So actually, I will do an even simpler example today. I'm going to write the whole thing out. So here's a graph. Okay, it's actually a multigraph, but I'm happy with that. I don't mind multigraphs. And let's call these edges A, B. So does anyone want to tell me what the Kirchhoff polynomial of this graph is? Or what's a spanning tree of this graph?
Is it A plus B, the polynomial?
Yeah, it's a plus b. And then you would have an integral that looks like this. Well, I guess a plus b squared. But I said to set one of the variables to 1, so I get rid of that, and I just have a 1 plus b squared, and I'm going to integrate that b greater or equal to 0, db. Okay, and that's just a calculus exercise, so you could actually do that. Okay, let's do another example that I'm not going to actually, that is not so much a calculus exercise, a little more tricky. What if we had K4, and for me, my K4 has external edges, so there's extra little guys coming off all the vertices. Now, if you take the period for K4 and you actually do the calculation, it turns out you'll get 6 Riemann zeta of 3. And so that's kind of nice. And again, if any of you guys are secretly the kind of number theorist or special functions theorists who like Riemann zeta, then this is a pretty nice number. And these, I call it the period, and it may be not obvious why I want to call it a period. They're periods in the sense of Kontsevich and Zagier. And what does that mean? It means it's an integral of something algebraic over a region that's defined by polynomial inequalities. So it's sort of, you make everything, all the bits and pieces are algebraic, and then you get to integrate that. And that ends up being a very nice set of numbers. There's actually an extremely readable paper where they lay out this idea.
Just a quick question.
Yep.
Are all the spanning trees here, are you taking all the external edges each time? Or I guess that doesn't...
It doesn't matter. So yeah, I introduced these external edges, but now for the purpose of what I've defined here, they don't matter. The external edges come into what goes on if you sort of take the next step towards the physics. So if you actually wrote down the Feynman integral, this is basically the residue. There's a singularity, and this is its residue. But if you actually want to understand more about the Feynman integral, then you need to incorporate in, you need to incorporate in momenta for the incoming and outgoing particles. So you really need the external edges. You may also have masses, etc. So yeah, it was a little bit of a red herring, but it's part of the broader context that this question comes from.
I see. Thank you.
All right. So that's this is just a big empty page, but that was the point of this big empty page, is a little bit about what I was just saying, is that the period, so the Feynman integral, it depends on more things. And so it depends on the momenta of the external particles. Okay, let's get rid of that little thing. Depends on masses. Now, in a scalar field theory, that's actually all you need, but for non-scalar theories, then you also will have some numerator structure, and you'll now be summing over, well, everything will become tensors, and you'll be summing over some expressions in terms of them. And now, so the period PG is a residue. Okay. And it's special because it's independent of all these things. It's also independent of some choices that physicists make. They make choices of renormalization scheme and regularization scheme. And this is independent of that. But because you've taken away these other things, if you're actually doing the physics, there's more than one source of complexity, basically. So for physics calculations, there are multiple sources of complexity. And so if you have a lot of external particles, that's the physicists would say lots of legs, then that makes your integrals more complicated, your answers more complicated, what kinds of functions show up more complicated, etc. So one of the cases is the lots of legs. If you have internal masses, then if they're all the same, that's relatively easy. If you want to have potentially different masses on each particle, that's more complicated. So there's issues with distinct masses. But then there's also just, even if we fix the number of external edges, there's just a case of how big the graph is. And that in the physics language is saying that there's lots of loops. Okay, so now I need to tell you what a loop is to a physicist, because it's not what you're thinking as a graph theorist. Well, loop very roughly means cycle. Well, not very roughly. It does mean cycle, but there's a particular thing that the physicists will say. They'll talk about the loop order. And what is the loop order? It means the dimension of the cycle space. And that's the most useful measure of how big a graph is in this world. Okay, I think most of you don't care about that. So let's go on to think about this actual integral. Now, the denominators are important. They're really what's controlling what's going on with the integrals, and it doesn't matter too much sort of which hat you're viewing this world with. If you're viewing this with your algebraic geometry hat on, then it shouldn't be too surprising, because if you're thinking about it in algebraic geometry language, you want to say something like, okay, I've got this polynomial, and it's the variety that's the vanishing of this polynomial is going to be telling me where my integral could be having weird things going on, and then this number, this period, is in fact some period of that variety. And so you should expect the geometry of that variety to matter, and so that polynomial matters in the sense that it ever can matter in algebraic geometry. But if you're coming at it from a combinatorial or graph theoretic perspective, then what you want to be noticing is, well, it's really just some sort of multivariate generating series for spanning trees. So we're really just counting spanning trees the right way. And now what's nice about this is, as you do the integrations, you continue to just count spanning trees in the right way. So let me sketch out the first 5 integrations. We saw that it starts by looking like this. And by sketch, I mean I'm going to write it in this way that won't get me marks in my calculus class. Okay, now if I do one integration, what's going to happen? Let's say I integrate edge. Oh, I said I was going to set edge 1 to 0. Well, 1 to 1. Never. Let's just we'll just pretend I didn't do that. So at the next integration, it actually ends up being a contraction deletion situation, because what do I have here? I end up having G with the edge contracted and G with the edge deleted. And this actually is a little calculus exercise. So this is one, if you're bored, you can think about this for a moment, remembering that psi here was the sum over the spanning trees, and it was the edge not in the tree. So if I fix any particular edge or edge variable, this is a polynomial that's linear in that variable. And so this is really just the integral 1 over some linear polynomial squared with respect to that variable. And so that really is a calculus exercise. And what are you going to get? The 2 things that will come out once you take your limits are the part that was the coefficient of that polynomial and the part that was the rest, what you got if you set, sorry, the coefficient of that variable in the polynomial, and the part that was the rest, the part you would get if you set that variable to 0 in the polynomial. And if you think back to how the Kirchhoff polynomial was defined, those are the contraction and the deletion, or the Kirchhoff polynomials for the contracted and deleted graphs. Okay. Well, that's sort of nice. And now, what happens next? Well, what happens next? Well, you get some logs up top. You can write them down explicitly, but I'm not going to write them down explicitly. And now you get something where you get to contract. Oh, I just called it E. Let's call it E1. Let's change it to E1. Now I can contract E1 or E2. And then what do I want to pair that up with? I could delete the E1 or the E2. And I could contract the E1 and delete the E2 and vice versa. Well, it turns out, and this is actually a little classical thing, this is a Dodgson identity, that this has another expression. This is actually just a square of another polynomial, which I'm going to call psi1 comma 2. And this polynomial is also really just about spanning trees or spanning forests in this case, but I'm not going to give you the exact definition today because that's not really the point of this talk, and I want to get on to the results of this talk. And so then you can go on from there. So what happens with the next integration? You still get logs. You get another expression on the bottom, which I'm not going to write out, but it's still an expression in terms of spanning forests. So these are all polynomials defined as sums over certain spanning forests. And now at the next step, you get a dilogarithm over more of these things. And then, well, it keeps on going, but something interesting happens. So the next step, this is the fifth step, you get some trilogarithm stuff over some things here on the bottom. But let's just count it out. So here, we integrated one variable. We integrated E1 to get here. We integrated E2 to get here. We integrated E3 to get here. We integrated E4 to get here. We integrated E5 to get here. And now we're at the end of what always works. So to here, it always works. But after that, well, it doesn't always work. And so that's where we need to understand what the general picture is. So after the first 5, so let's let dn be the denominator after the nth step. And notice this does depend on the order of the edges, but I'm suppressing that from the notation. Well, it doesn't depend on the order, but it depends on which edges you've integrated. So it depends on which edges you've integrated so far. But I'm going to ignore that. So what happens? If dn looks like this, a and then some variable ae, some polynomial like this, and it actually factors, not necessarily into a square, to something like this, then dn plus 1 is ad minus bc. So these capital letters, the a, b, c, and d here, they're representing some polynomials in the remaining edge variables. So if there is one choice of edge variable, then where it factors into 2 linear factors, then if I integrate that edge variable, well, maybe I'll just expand that in case anyone's going to look at this later. So then integrating the edge AE, the next denominator becomes AD minus BC. So that's kind of nice, but that doesn't always work. So if dn doesn't factor, well, you're toast. I mean, not quite. There are tricks, but you don't have this nice general algorithm, not this version of it anyway. If dn is a square, then the next one is 0. And so this algorithm stops, but in a slightly different way. So also the algorithm stops. So this is the denominator reduction algorithm. And furthermore, I want to emphasize that so far it just feels like polynomial manipulations. But these polynomials will typically also be in terms of spanning forest polynomials. So still, typically, all these polynomials can be defined in terms of spanning forest polynomials. Defined as sums over spanning forests. Appropriate spanning forests. So it's actually a big game about spanning forests and different kinds of spanning forests as you process edges. And you saw contraction deletion coming up, but this is also sort of a contraction deletion thing, because we take the contraction from one factor and the deletion from the other factor, and that gives you one of these, and then the other one gives you the contraction from the other factor and the deletion from the other factor. So this is also a contraction deletion step. Okay, well, no, that's not what I want to do. So the reason I gave a lot of background on that is because the result I want to tell you about is using a generalization of the denominator reduction. But first I want to tell you about something else that's really close to my heart, which is this C2 invariant. So what is this C2 invariant? I didn't actually need to tell you anything about denominator reduction to tell you about this C2 invariant. What do? You take this polynomial, this Kirchhoff polynomial, and what do you do with it? Well, I said you could put on your algebraic geometry hat, and then you might care about the geometry of the variety of this polynomial. And now one of the things you could do while your algebraic geometry hat is on, you might say, well, I care about the geometry, but I'm having trouble, getting what I want. So let's do something easier. Let's look over finite fields. And so this notation is just my notation to say I want the number of points over that finite field. So I'm counting the FP rational points if you're thinking in that kind of language, or just operationally, a finite field is, well, finite conveniently. So just plug in all the possible ways of plugging in the values of that finite field into the variables of the polynomial, and count how many times you get 0 modulo p. So number of points on psi g over fp. Okay, now it turns out that as long as your graph has at least 3 vertices, this is always divisible by p squared, and then we're going to take that mod p. And so that gives me, for each prime or prime power p, it gives me a number, or a number modulo p. Okay, so I like this, and some of you guys know why, because you've heard me talk about it before, but let me just outline why, in general, why you might care about this. So there's going to be 2 columns of why. All right, so this was the motivation, is that originally, so all the Feynman periods, so the PG calculated, were multiple zeta values. Okay, and if they're all multiple zeta values, well, you hope it's not just some sort of weird cosmic coincidence, but you hope that there's some good mathematical reason why they're all multiple zeta values. And, well, if you're Kontsevich, then the good mathematical reason that ought to be there should be because the varieties, if you like, of these polynomials, or you're thinking of it in more sophisticated ways on motives of these polynomials, they should be the right kind of thing, and they should be mixed tape motives. So it should be for this good mathematical reason. Okay, but then that good mathematical reason would have consequences. And one of the consequences is it says, okay, the geometry of those varieties is super nice. It's this particular nice thing. And in that case, the point counts over the finite fields would also be super nice. And in particular, so this would imply that these guys are polynomials in P. Okay, that's interesting. Now, it turns out that this is false. I mean, it's not false that originally the ones that were calculated were, but the obvious conjecture is false. They're not all multiple zeta values. But this ends up still being an interesting idea because, well, and in this case, let's just go back to this, that these are polynomials in P. So then C2 would be the quadratic coefficient. And that's actually the 2 in C2. And because we said as long as the graph has at least 3 vertices, there's no constant or linear term. So it is in fact the lowest that's potentially non-zero of the coefficients. And so in particular, C2, if it's the quadratic coefficient of this polynomial, then it's not dependent on P, right? C2 is actually C2 of P. So this would be independent of P. Okay, so it turns out it's not true that they're all multiple zetas. So originally all the ones calculated were, but this is false. Okay, but if you come down here, the extent to which it's not a constant becomes an interesting measure of how false it is for any particular graph. So how much C2P is not constant is a measure of how sort of non-multiple zeta value PG is. And so this ends up being really interesting. And if I give a talk about this for number theorists, I'll say something about how, well, some of them are coefficient sequences of modular forms and blah, blah, blah. And it's very interesting. And there's also lots of interesting sequences too. So if you like sequences, Oliver Schnetz has done a bunch of computations of C2 invariants. And some of them they can recognize. Some of them you can just see right off that they're constant, or that they just depend on, what's going on modulo 4 or something like that. So some just small field extensions. And other ones with a bit more effort, you can see that they're coming from modular forms. But then there's some unknown sequences. So if you like unknown sequences, I can show you some nice ones. Okay. So this is why someone who's not me might care about this. And this is why lots of people got interested in this. But now there's another reason you might care. So now that you've decided this is an interesting thing to study, we notice that these are somehow combinatorial. So also, well, the C2, it can be calculated by counting partitions of the edges of G, well, not quite of G, I have to deal with a few edges especially, but basically of G, into, well, what do I really need to do? I actually need P minus 1 copies of the edges. So partitions of P minus 1 copies of the edges of G into P minus 1 spanning trees and P minus 1 spanning forests of a particular type. And I'm pretty sure I gave a talk in your seminar 2 or 3 years ago where I talked about this, and I talked about proving a very small special case of a particular conjecture. And I think this is great because it turns these things, which sort of sounded like big fancy algebraic geometry things, it turns them into really nice counting things, and also very sort of graphy counting things. I think this is super beautiful. And in fact, as a brief update, if anyone actually did remember when I talked about that conjecture, I proved the P equals 2 case of a conjecture, but not the whole even P equals 2. I proved P equals 2 and when the graph had an odd number of vertices. And one of my master's students has now proved the even case. We still can't get past P equals 2. You can maybe guess why. All right. What else is cool about C2? So another piece of this story that some of you will have heard me tell you about before is that there are a lot of graph symmetries that, well, there are a lot of graph operations that C2 is symmetric under. So, well, let's start with duality invariance. Right, so if I have C2, well, and it's true for all P, of a graph, and C2P of the planar dual of the graph, they're the same. And that's also true of the period. So PG is also equal to PG star. So that's kind of nice. Now what's completion invariance? Completion invariance, now that's the one I was talking about, the conjecture last time I talked to you guys. So it's saying that C2P, you remember K? K was the 4 regular guy. So it doesn't matter which vertex you remove. You should get the same answer. So that's a conjecture here, but it's proven, the analogous thing for P is proven. So here it's a conjecture, but if I say P of K minus V equals P of K minus W, that's proven. And these are some other interesting symmetries. So there's a twist invariance. Twist has a cool picture, looks like this. So if this is your completed graph, the operation is to move from this guy to this guy. And many years ago, some of, well, I guess faculty who've been around at SFU when I was there and remember Ian Crump probably saw that picture because his thesis work, his PhD thesis work involved a different invariant that was symmetric under those. And I think I'm not going to, no, I have to say something about double triangle invariants because I saw Mohammed in the audience. Double triangle is this operation, where you take a triangle and now you split it. So now it's 2 triangles. Like that. So that's a C2 invariant. So if that occurs somewhere inside your graph, here and here, then the C2s are equal. Okay, and it's conjectured that if 2 graphs have the same period, then they have the same C2. The converse is definitely false. There are special cases when the C2 is 0, when the C2 is -1, that we at least conjecturally have an idea of what's going on with the period, and they're not all the same. But this is still a very interesting conjecture. Okay, I believe, what else was I saying? Oh, yeah, sorry, I already said that. I just said that off to the side, that C2 can be reformulated in terms of counting partitions of P-1 copies of the edges into spanning trees and appropriate spanning forests. And so this means it's a counting object, and that's part of what I like about it. So I'm just going to write yay because I like that. Yeah, that's a different talk. Okay, that's the big background of this story that I've told you guys before, and that you could list through about half of my students who've worked on various aspects of this, and I've worked on various aspects of this. That's the end of that portion. And with my last 15 minutes or so, or I guess only 10 minutes or so, I want to tell you about something new that's a little technical, but I think also kind of nice, and that's where you'll get the hourglass chains. Before I do that, are there any questions? All right. So remember the denominator reduction. I'm just going to scroll back. I don't want to do this too much because I know it's can be a little bit nauseating. So let's just go back. Where was it? There it is. This was the denominator reduction. It said this. I'm going to put it in a cloud. So if your denominator factored, you could make the next one like that. Now that's nice, and it actually comes with a whole algorithm to do the Feynman integration. But sometimes you get stuck. And so Oliver, he recently, say, I guess in the last year or two, proved a really nice generalization. So we're going to, this is more going to be about C2 and calculating things like that. So we've got a P. And it's not going to work for P equals 2, but for P greater than 2, we basically want to work with the denominators squared. Oh, here's a detail which I really should have said. You can use the denominators in the denominator reduction to calculate C2. So that's really something I should have pointed out, is I gave the definition of C2 in terms of counting points on that original Kirchhoff polynomial, but you can also count points on any of the guys from the denominator reduction. And actually, they're better because you don't have to divide by P squared. And that sounds like a triviality, but that actually really helps. So you still get stuck, though. You still get stuck because your stupid denominator doesn't factor. And so Oliver says, aha, let's think in terms of denominators squared. And now we'll have 2 different ways to proceed. If at the nth step, it's actually just literally something squared, then you build this polynomial. If at the nth step, a square factor comes out and then there's like some chunk that's not so nice, then you can still go to the next step. And now notice, what does this look like? I feel like there's a typo. Yeah, there's a typo. This has got to be a D. There we go. That's one thing I like about these tablet talks, is when there's a typo, I can just fix it. So this is a D. And so notice here, really, what have I done? It's like you've solved this thing, right, for a n plus 1, and then you sub that in over here. That's actually what you've got over here. Okay, so now I have two things that I can do instead of just one. So that's kind of nice. And notice, if both of these are simultaneously true, then we're actually back in the original denominator reduction case. Right? So if these are simultaneously true, then it means there's this linear square factor, and then this thing also would have to factor into two equal, like it would also factor into a square. And then what do we have? Well, you're in here, but the A, B, C part is going to factor. So this factors, and this becomes a square, and it becomes exactly the square that you have from the regular, it becomes exactly the square of what you would have from the regular denominator reduction. Okay, so that's good. It does, in fact, generalize the existing denominator reduction. Okay. And now what I want to work on is let's do an example. Let's actually compute some C2s. And I'm going to compute these kind of quickly. And fortunately, most of the pictures are already drawn. So this is the family of graphs I'm interested in. And I imagine I've got some graph theorists in the audience, and I'm curious if any of you have any particular thoughts about this family of graphs. Sorry, this picture is kind of gross because, yeah, so here's just some graph. There's some graph in here. And then these are these little, they're triangles that are joined at vertices. And I'm calling them hourglasses for obvious reasons, because they're like little hourglass shapes. And so I join them together. I join these hourglasses together at vertices, and they go all the way around. This chain of hourglasses. Now, do you remember this decompletion thing where K was 4 regular? So this guy's 4 regular, right? I mean, assuming the blobby part's appropriate. This thing is all 4 regular. So it's my K. It's not my G. So I have to choose a place to decomplete, and I'm going to choose this. So by calling this infinity, I mean this is the vertex I remove when I go from K to G. Okay. And now we had this process, this denominator reduction process. And I told you could always do 5 edges. And then if things factored, you could keep going. And so in this particular case, I can start by doing these edges. So I do for the 5 edges, 1, 2, 3, 4, 5. And then it turns out that it factors appropriately to also do 6, 7, and 8. And then after that, in fact, it also factors so that I can do the 6 green edges. These are not maybe the most obvious ones to start with, but they work well. So I'll reduce these green edges next. When I talk about reducing an edge, I mean use the denominator reduction algorithm. So then by conventional denominator reduction, you obtain the following picture. And now I need to explain what my notation means here. So if I just draw a graph like this, this means, so just drawing a graph means it's Kirchhoff polynomial. I should write more neatly than that, shouldn't I? Now, here's something else. Here I've drawn a graph with some colored blobs. Actually, I'm going to circle the next one because I'm going to want to circle something else about that. So a graph with blobs, a graph with some colored vertices, is an analogous sum over spanning forests And I kept talking about these spanning forests, and I never told you which ones. Well, now I'm going to tell you which ones. They're the ones where there's exactly one tree for each color, and the vertices of that color have to be in that tree. So I'm just going to say one tree per color, but you have to add in that last part. It's bijective in the obvious way. Okay, and now what does this mean? What's this product over I? Well, it turns out that one of these parts of the hourglass chain just completely disconnected. And so this I is going through the different, the I is indexing the different hourglasses of the hourglass chain. Now they look like bow ties, but anyway. And then the final note is that this, remember, this started with something that was Kirchhoff polynomial squared. So you should expect every variable could appear squared in this whole polynomial, at most quadratically in the whole expression. So this guy is in the same variables as the other pieces. Right? So for instance, this triangle is the same as this triangle in the sense they have the same edge variables, because one of them was coming from one factor of the original Kirchhoff and the other was coming from the other factor of the original Kirchhoff. Okay, well, with that all in mind, let me tell you how this calculation goes. So, okay, we label some things. I'm just going to scroll through this. In fact, I'm going to put myself back because I think I have almost no time left anyway. So I can just scroll through this. Going to label it like that, and you reduce x, and that works. You get something. You can also make the y's and z's explicit. And now this is the point that at conventional denominator reduction, you're stuck because it doesn't factor into linear factors in any of the variables. Okay, but we can do the quadratic denominator reduction, and that's what you do. So you do quadratic denominator reduction. That's why everything is squared, and the y is gone because you reduced y. But now if you look at this expression, you see a bunch of z's factor out, right? There's a common factor of z here. Then there's two z's over here, so you're going to get a z squared factoring out, and so you can reduce z. Okay, and you reduce z, and you get this guy. This -4 explains why it doesn't work with p equals 2. And that kind of thing will happen in general. Okay, now you keep going. You can reduce the bottom triangle. Some stuff happens. You have to do some work. But what happens in the end is that you do a bunch of work, and you do a bunch more work, and you have notation to make the horrible work work. And then it goes on. And it's actually kind of hideous. Did I tell you it was technical? Okay. But now the magic happens. There's a square factor. And I have to say, I didn't anticipate this guy was going to be here. And I don't really know a deep reason why. I mean, I can prove that it happens because all those things I just scrolled through quickly, those are rigorous calculations. This guy does show up here, but I don't really know why. So why? And then you can continue, and this last line is just what it should be. Okay, so there's the square factor. It comes from this pair of hourglasses, and you get rid of it. And what you end up getting is the same expression as before, but with one hourglass gone. Okay, induction. So you use induction. You consume all of the hourglasses, and all that's left is, okay, that, which looks kind of gross. But notice, all that there is the blob. Here's the blob. And only ever one hourglass. So one hourglass leaves some sort of guck behind. Okay, then you give it to Oliver, and he actually tells you how to get rid of all that guck. So you can finally express an answer just in terms of different spanning force of that original blob. All right, so I went a little bit over. So this is my conclusion. I think C2 is awesome. And I think all these things are a lot more combinatorial and graph theoretic than you would think if you just asked a physicist. And this particular calculation is something new that I hope the people who've seen a lot of this story before will find interesting, using this new version of denominator reduction. All right, I will stop there.
Thank you so much for your talk, Karen. I wonder if we can all unmute ourselves and give her a round of applause. All right. I will also open the floor if anyone has any questions about the talk.
I have a question. Luis here.
Yep.
Yeah, so if we scroll back to the slide just before you started your example, just before you, yes,
Yeah, the example that we just sort of
yeah,
went through and you didn't actually see.
yes. So just a little more.
Yeah, we're getting there.
Yeah, coming this one, this formula here.
Yep.
I'm curious because, uh, and in the second equation there, you have a times little a sub.
Oh, yeah, that's another typo. I'm sorry. There's too many typos in here. Isn't
Yeah,
there?
I
Yes.
just was wondering.
Thank you. Good comment.
Okay, I
It's meant
couldn't
to be.
figure out how
Yeah,
you lost
yeah.
symmetry.
I wrote it a little too fast. Yeah.
Great, thank you.
Sorry about that.
That's all. Yeah,
Good eye.
very nice talk though, Karen. Yes. Yeah, that makes sense.
Are there any other questions?
I have one more question. Is there a natural class of graphs that now that you can solve now with this technique that you couldn't do before? I mean, you described one.
I mean, I described one particular class.
Yeah.
I don't know, like
maybe degenerate ones.
I don't have a nice characterization. Here's a family that we could do, and obviously that's not the class of graphs that are integrable with this technique. But I don't have a better characterization.
Right. Thank you. That's very nice. I'm assuming it proves a conjecture for this class of graphs also.
No, it was just a class we could do.
Oh yeah.
I mean, there are some things that are interesting about it that I didn't really say, which is that because you can kind of put anything in this kernel, it means that you can get infinite families. You just make the kernel so that the C2 is what you want it to be, and then you automatically get infinite families with that C2. Okay,
Right.
That's not super deep. And if they had triangles, you could already do that with double triangle, but it's another way of doing it.
Mm-hmm. Me.
Have you guys seen, you graph theorists, have you seen chains of hourglasses like this? Are they interesting to you guys at all?
They remind me of diagrams that Boyan had about graphs with crossing critical characterizations of crossing critical graphs have ears like that. So graphs which have a certain crossing number, but if you delete an edge, and the crossing number decreases by at most one. It has chains that look very much like that. So you might want to run them by Boyan.
He's not here, is he? I don't actually know who's here.
I don't think so.
Karen,
Yeah.
it's Amarpreet talking.
Hi.
Hi, how you doing? Is there something? Do you have like a preprint or anything for this?
No, we need to write it up. If you really,
Okay.
if you really want it, I can send you some like notes that are not for broad circulation. The basically the proof is written up, but yeah, I don't know. It's have you noticed it's been a bad time? I have not been very productive lately. So
Something going on. I don't know
a
what it
draft of
is.
it on the train. So I went to visit. I was in Germany for 8 months on a Humboldt fellowship, and I went to visit Oliver in Erlangen. And on the way back from Erlangen to Berlin, I wrote, like we figured out this calculation the week I was there. And then on the train on the way back, I was like, I'm not going to have a chance to write this down. I better write it on the train. And there's a version of this that I wrote on the train, and that's all we've got. And that was now over a year ago. So we have to write it into a real paper.
Okay, but okay. So how about not your stuff, but the background to this material?
Oh yeah,
like...
there's lots of things I can send you for the background. Sorry, I was thinking of the hourglass chain specifically.
Okay.
Which part are you most interested in? So
I guess you were talking about just the computation, like the intro stuff, like this computations of PG and what happens with those computations of PG and what happens to those denominators in general. Yeah, like some of these things here.
Yeah. Okay.
Same.
Yes. Yes. Maybe in terms of in the sort of language that I say it, I wrote a little tiny book, like a little mini book, and I can send you that. And then, yeah, I think I would cover most of what I talked about in the introduction.
Is it on your webpage or?
Is the link to the book? I think so. Here, I will put it in the chat. Just let me stop sharing, and I will put. Okay, yes, that worked. And now I will put in the chat. I will find it and put it in the chat. Just give me a moment. Oh, I see there's other questions in the chat, and I'm sorry, I wasn't following the chat as I was reading.
Okay, thank you, Karen. Thank you.
And I'll answer a question from the chat. So there's a chat, and I realized I talked about dialogues and trilogues, and I didn't tell you what they are. So the dialogarithm is a classic special function. It's one of those ones that in a different world, they might have been one of the sort of the next ones. So they actually come up a fair bit, but they're not sort of part of the standard undergrad curriculum. And then there's actually these generalizations to these to polylogarithms. So you can go from a dialogue to a trilogue and a four-log, etc. The dialogue is the only one that's like really classical. So if you get one of those old special functions books that has all the wonderful integrals that are actually kind of gross, but sort of wonderful in their own way, then you'd find the dialogarithm in there. And it's a family of special functions.
Okay, thank you, Karen. If that is it for questions, maybe we can